Now you know what all these variables mean. Now look at this equation. Compare it to the spring equation. Minus kx equals m d squared x dt squared. In that case, the solution, the most general solution, was x equals a sine omega t plus phi. Well, these two equations are exactly the same. They're exactly the same. We just changed the letters. That's all. K is, whoops. Let me change my color again. Come on. This is K. This is M. I don't know if that's obvious. Here we go. This is M. This is K. And X is theta. So as long as we take the solution to minus kx equals m d squared x dt squared, and we change all the x's to thetas, we change all the k's to rmg's, and we change all the m's to i's, then the solution must be correct. Theta is equal to a. Remember, a is just is to do with initial conditions. It's not to do with the physical constants. Sine omega. Okay. Remember that omega was the square root of k over m. Whoops. Let me write this on a new page. There we go. Now, omega is square root of k over m. I forgot to write that down. So now we just change our variables. X is theta. A is just the amplitude, is the maximum theta. Sine. K is RMG. RMG. M is I. And T is time. And phi is still just the phase. It's just dependent on the initial conditions. What is theta when t is equal to 0? Gives us phi. And so this is the solution to the physical pendulum. This is the equation of motion for a physical pendulum. Theta is equal, well, there you go. That's the solution to the physical pendulum. Now, remember what this is. This is omega. Omega equals the square root of RMG over I. And that is equal to 2 pi f. So therefore, the frequency is 1 over 2 pi square roots of RMG over I. And therefore, the period is 2 pi square root of I over RMG. Okay, so that's the period for the physical pendulum. That's how long it takes for it to do one complete cycle. All right, so let's go ahead. Now that we understand the physical pendulum, we can apply this to the simple pendulum. Remember, the simple pendulum is a single mass M at the end of a string of length L, a massless string at length L that pivots at point P. And so now we can compare the physical pendulum to the simple pendulum. For the physical pendulum, the distance between P and the center of mass of the system was R. For the simple pendulum, let's make sure we know what the simple pendulum is. As a reminder, right? I just said it. Point mass, the end of a massless string length L, pivoted around a point P. Okay. And so if we compare that to the physical pendulum, the center of mass of this system is at the point mass because it's a massless string. And so therefore, R from the physical pendulum must equal L for the simple pendulum. The moment of inertia from the physical pendulum, we know the moment of inertia of a point mass at a distance L from the pivot point P is mL squared. That's the moment of inertia of a point mass at a distance L from the pivot point P. And what else is there? RMG. That's it. So what we end up getting for the simple pendulum is theta, not x. Theta is A sine omega t plus phi, where omega is square root of RMG over I, which is now, for the simple pendulum, L mg mL squared, which is the square root of G over L. And you've probably seen the simple pendulum before, and you knew that the angular frequency was square root of G over L, which gives us that the period of the simple pendulum is 2 pi square root of L over G. The period of the simple pendulum is dependent not on the mass at all, which is really interesting about the pendulum, the simple pendulum, is that the period of oscillation, you can make that mass as big or small as you want, the period of oscillation is still the same. Doesn't matter. It's dependent only on the length of the pendulum and the acceleration due to gravity. So let me talk about an example, and we really already addressed this a little bit when we talked about springs, but how does a clock work? Right? How does a clock work? A clock has to have some sort of oscillator in it. It's got an oscillator in it that repeats itself, and your typical, stereotypical kind of clock is either a mass on a spring, right, something really small, or a pendulum. And so your typical wind-up watch, we already talked about, is a mass on a spring. It's just a different kind of configuration. And then the grandfather clock is the pendulum, is the kind of pendulum that swings back and forth. So either one can be used as a timer. So let's just talk about if I wanted a pendulum that swung back and forth that had a period of 1 second. If t is equal to 1 second, we figured out what kind of mass and spring we needed when we talked about mass and springs. But now let's figure out what should the length of the simple pendulum be. Pendulum. Okay, well, that's just t equals, it's actually just a plug-in, right, as many of these things are. T equals 2 pi, square root of L over G equals 1 second. So therefore, 2 pi squared L over G equals 1 second squared, and L equals G times 1 second squared over 2 pi squared. G is 9.8 meters per second squared. And whoops, hold on a second. Right, I had to think about my units. Since G is 9.8 meters per second squared, the second squareds cancel and we're left with meters. So the units work out. Let's go ahead and plug in. And the answer is 0.25 meters. So all I need is a quarter of a meter of string with a mass on the end, and that should be a good clock. 1 second. Now, of course, what happens when you start that oscillating? First of all, let me come back to that question. But first of all, remind you that this is small angle approximation, so we don't want to pull it very far from equilibrium. But we can go ahead and we can hang this pendulum right from the ceiling, make L equal 0.25. And we can pull that up from equilibrium as long as we don't pull it much more than 10 or 15 degrees, and it should oscillate back and forth with a period of 1 second. Now, what mass should I put on there? Right? It's independent of mass. That's a little surprising, but it doesn't matter what mass I put on there. We might want a somewhat heavy mass in order to reduce the effects of friction. And of course, so I come back to the question, if I really want to create a clock, what happens if I create this pendulum is it comes to a stop pretty quick because of friction. So I need to drive it. I need to give it a little push every time. And this is the way grandfather clocks work, is they're given a little push every time they pass equilibrium so that they keep oscillating back and forth. Okay, let's do an example problem. Let's do a simple pendulum with length 0.7 meters and mass 0.5 kilograms, is given a push from equilibrium, so the initial velocity from equilibrium is initial speed is 4 meters per second. What is the and then ensuing motion is simple harmonic motion. What is the amplitude of the motion? A, and what is the equation of motion? Theta versus t. B, part B. I made up these numbers, so if V is too big, so it gives us too large an angle, we'll just ignore the fact or we'll just recognize that we have gone past the small angle approximation, and so our theta versus t is not perfect. But let's just see what happens. So how do we do this problem? Well, there's actually two ways we can address this. We can address this just by writing down the equations of motion, which we already know. Let's go ahead and write down the equation of motion, right? Theta equals theta max, right? The amplitude, or we could make that A, but I'll just write it as theta max, sine times simple pendulum, square root of g over L, t plus phi. Okay, so that's the general equation of motion. We also know that, oh, whoops, never mind. I made it a little bit more complicated than I meant to because I gave a initial velocity, but we're talking about angular variables. We know that theta dot, which is omega, theta dot, right, d theta dt. I tend not to use theta dot. D theta dt, not theta dot. Same thing as theta dot, whatever, is omega, and that is equal to, ooh, careful. Okay, angular velocity is different than angular frequency. Let's not use omega here because that's just going to confuse somebody, even though we should be able to deal with it. Let's just say d theta dt is the angular velocity. Theta dot d theta dt, which is the angular velocity, is the time derivative of this thing, which is theta max times the square root of g over L times the cosine of the square root of g over L t plus phi, and the second derivative, which is theta double dot, which is d squared theta dt squared, which is the angular acceleration, or alpha, is theta max times g over L times sine, there's a minus, I always forget that minus sine. When we take that derivative of cosine, we get minus the sine, and there. Okay, so those are our equations of motion. I didn't write them down before because it's the same as for x. It's the same equations. We just, instead of x, we're using theta. Instead of omega equals square root of k over m, we're using omega equals square root of g over L. So here's the confusing part, is that I gave you an initial velocity, and so we would have to turn that into an angular velocity, right? I gave you a initial speed, and we'd have to turn that into an angular speed, and you need to remember, in order to do that, that angular velocity is equal to v over r. And so, therefore, that initial angular velocity is equal to 4 meters per second divided by 0.7 meters. This is reviewing rotational motion. So therefore, we could go ahead and take that angular velocity equation and say that the angular velocity, theta dot at t equals 0, is equal to whatever the theta max, square root of g over L, cosine square root of g over L times 0 plus phi. And we know the angular velocity, right? This is the angular velocity. That we know is, I'm going to write an arrow all the way across, right? That's that. We know we know G, we know L. What we're looking for is theta max. We want that. Do we know phi? Do we know what phi is? I left that off, right? We could have figured that out to begin with, right? Theta is equal to theta max. Actually, I'm not sure I need to write anything down there. Do we know what phi is? We do know what phi is because at initial conditions, right? Our initial conditions are at t equals 0. What is theta? Right? So we always figure out phi from initial conditions. It always comes, the phase factor always comes from initial conditions. So we just say at t equals 0, what is theta? At t equals 0, theta is 0. So if at t equals 0, theta is 0, then we can plug that into theta equals theta max sine square root of g over L times 0 plus phi, and we solve for phi, right? Because theta is 0. Sorry. Yeah. Okay. And we solve for phi. So in order for the sine to be 0, the argument has to be 0, and so that means phi has to be 0. Okay, so we get the phase is equal to 0 because of the initial conditions at t equals 0, theta equals 0. That comes from the first equation.